Let's consider a problem where we want to compute the isentropic turbine efficiency. So you can imagine that we're given some steady state turbine, and the idea is that we want to compare our turbine, shown there, with an isentropic turbine. So basically we want to know how well our turbine compares to an isentropic one, and we'll cast that in terms of an efficiency. These problems, mathematically, are pretty straightforward. The calculation is very simple, but you have to figure out how to correctly compare the two turbines, and that's the tough part. So we'll go through that in detail. In this case, let's consider ideal gas air moving through the turbine, and we'll ignore kinetic and potential effects. Furthermore, we're told that the amount of work produced per m dot, namely W dot over m dot, is 30.3 kilojoules per kilogram. So all we've done is factored out the timing and made it into a mass rate instead of a time rate of energy delivery. Okay, so the turbine is outputting that to its environment. We're also told the inlet conditions, and remember, with a lot of these entropy problems, you can either label things inlet with an I or just state 1 because the stuff is moving through the inlet to the exit and changing. So we'll call it T1, that's the inlet condition, is 400 Kelvin, inlet pressure is 5 bar, and we're only given the exit pressure of 3.45 bar. The way this works is that that value of 3.45 bar, the exit pressure, is our anchor point that forms a basis of comparison between our real turbine and the isentropic turbine. Because you can imagine there's a whole host of isentropic turbines you could compare to. We want to compare to one that produces the same exit pressure so that at least we're not comparing totally dissimilar objects. Once we fix that, as we'll see in a minute, we can come up with a well-defined efficiency. Okay, so the efficiency of an isentropic turbine is given in your lecture notes, and it's the ratio of W dot over m dot for the regular case, so the numerator of this we actually have, that's just the turbine that we built, and that's divided by W dot over m dot for the isentropic case. So that little S subscript means S is being held constant, that's isentropic. Okay, so the tough part of this is figuring out the denominator. We're given the numerator. So what do we do about the denominator? Well, again, if you look in your lecture notes, you'll see that this quantity is just a difference in specific enthalpies, as long as we can ignore kinetic and potential effects. And so in that case, W dot over m dot at constant entropy is H1 minus this quantity H2S. And so this is where we're trying to construct an isentropic system, and so H2S ultimately will be determined by that final pressure P2, and we'll see how in a minute. As for the value of H1, well, we can look that up, right? So if we want to know H1, we have the inlet conditions, we have the temperature and the pressure. Honestly, you only need the temperature. It's an ideal gas, so if you look in table A22 in the back of your book, the ideal gas properties of air, you can find the value for H1, and I'll write it over here on the left. It's 400.98 kilojoules per kilogram. We'll use that eventually, so I'll write that there. The next step, of course, is to figure out what to do with H2S. All right, so here's where we use these weird pressure ratios. And so one of them in your lecture notes is P2 over P1 equals this new weird variable PR2 over PR1. So, things you need to know about the PR variables. One, they're not pressures. I note this in the lecture notes explicitly in bold. They don't have units of pressure. They are in fact unitless. They're exponentials, so that means they're unitless automatically, and they involve the s degree functions, so it's kind of a complicated thing. The reason you get this simple ratio is that you go through and do all the stuff that we already know about an ideal gas, consider an isentropic case, and you can derive these very simple ratios because we've sort of subsumed all the complexity into this PR variable that you can just look up in a table. So ultimately, if you learn how to use them, it'll save you a lot of work, but they're a little confusing the first time. Now, how do we actually want to use them in this context? Well, we can look up PR1, right? Because we know all of the inlet conditions. We know the inlet temperature, the inlet pressure. So if you look at table A22, you go down to the temperature of 400 Kelvin, look over to the right, you'll see an entry for PR. The PR value is 3.806, and remember I said it's unitless. Let's write that over to the left so we don't forget. Okay, we've got that. Now what we want to do is, since we know P2, P1, and now PR1, we can solve for PR2. So we can find this other weird variable, PR2, find its value. So let's do that. All right, PR2 we just rearranged as PR1 times the ratio P2 over P1. And we know the other three values, so let's plug them in. And we'll get a value of PR2 equals 2.626. All right. How is that useful? Well, the way it's useful, and I'll write the value over there on the left for PR2, now we can look in the same table, table A22, and see if we can't find a value of PR2 equal to 2.626. So we look through, and sure enough, there is a value equal to that exactly, and it corresponds to a temperature of 360 degrees, But more importantly, the corresponding specific enthalpy for a PR2 value of 2.626 is 360.58 kilojoules per kilogram. I'm going to write that over on the left and label it H2S. Let me just walk through the logic again. The idea was, we knew that we wanted to have an isentropic process that ended up with the value of P2, 3.45 bar. We also knew the inlet conditions, 400 Kelvin, 5 bar. We could use this pressure ratio, P2 over P1 equals PR2 over PR1, because that corresponds to an isentropic process. We could go through and solve for what PR2 had to be, and then look at the corresponding specific enthalpy to figure out what the specific enthalpy for an isentropic turbine process was. Okay, so we just did all that. Now we have our value of H2S. Well, now the math is really easy, right? Because all we need to do is plug in our value of H1 and our value of H2S into that expression for W dot over M dot at fixed entropy. So let's do that. All right, W dot over M dot fixed entropy is H1 minus H2S. We put in those two values, and I'll move that up to the top. You can take that difference. It comes out to be 40.4 kilojoules per kilogram. So the goal of all of this, remember, was to take the ratio between our actual value of W dot over M dot, 30.3 kilojoules per kilogram, and this one we just calculated for an isentropic turbine, 40.4 kilojoules per kilogram. We do that, 30.3 divided by 40.4 gives you 0.75. So what that tells us is that the turbine that we built is 75% efficient. Its efficiency is 0.75 relative to an isentropic turbine that hit the same exit pressure given the same inlet conditions.